Hey everyone, my name is Bhaskaram, and in this video we are going to talk about flicker noise, or it's also called 1 by F noise. So the first thing I want to talk about regarding flicker noise is that it's most prominent at lower frequencies. So a typical noise profile might look something like this, where you have contributions from flicker noise at low frequencies, and then that contribution rolls off, and then you have contribution from thermal noise, which is white in nature and goes up to very high frequencies. So another thing about flicker noise is that it exists in ordinary resistors, and it also exists in BJTs and MOSFETs. However, when we compare BJTs and MOSFETs, the flicker noise effects or is more prominent is in MOSFETs as compared to BJTs. So as an example, for a typical BJT, the flicker noise corner might be in the range of like hundreds of hertz, but for a MOSFET, it's a bit higher, and it could be in the kilohertz to a megahertz range or more. So now let's talk about the cause of flicker noise. And I must add a point here that the cause of flicker noise is not, let's say, extremely well understood. But there are certain explanations from, people have tried to come up with papers that have certain explanations about the cause of flicker noise, and they have tried to come up with expressions. But so far, I haven't seen a very, clear and concise consensus on the cause of flicker noise and the expression for flicker noise. And if I can plug in numbers to that expression, then I get like a very accurate number of nanohertz or nanovolts per hertz of how much flicker noise I'm going to get at a certain frequency. That sort of stuff I haven't seen so far, but there have been explanations, and I'm going to show you one of the more common explanations for flicker noise that I've seen in textbooks, and it's called the charge trapping phenomena. So let's talk about this phenomena and how it might introduce flicker noise. So I want you to imagine an ideal silicon crystal. And the characteristic for a silicon crystal is that you have a silicon atom that forms covalent bond with 4 other silicon atoms. So let's pick any random silicon atom, let's say this one, and it's bonding to 4 other silicon atoms here, 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 and here, right? And so this pattern is the same throughout the silicon crystal. You can, this is just a part of the silicon crystal. You can, basically expand it on the top, at the bottom, on the right, and on the left. And once you keep repeating this geometry, you basically get a silicon crystal where each silicon atom bonds to 4 other silicon atoms. All right, so let's say hypothetically I have this silicon crystal, and it's too big for me, and I just want to cut it to a smaller size. So let's say I have this silicon crystal, and I'm like, okay, you know what? I am gonna cut it to a smaller size. So I'm gonna take just this portion, say this much. I'm gonna cut from here in the red dotted line all the way to here. So I'm just gonna cut out a smaller piece out of this crystal, and I'm gonna get a smaller size silicon crystal, right? And in my imagination, I might get some, after this cutting, I might get something like this, right? Where it's like smooth surfaces, and I've got a very clean block of silicon crystal. However, in reality, it's not as ideal. So what might be what might look in reality is, after my cutting procedure, is something like this, where the silicon atoms, when I cut the silicon crystal, we can't cut like bonds with such precision. And so what ends up happening in reality is that you might, during this cutting process, you might even displace some of the silicon atoms at the surface. So for example, here, let me show this in blue. So for example, here, this silicon atom was displaced, and you have a missing silicon atom in the structure over here. And then at the surface, you have this other silicon atom, which is also not in the regular geometry that is characteristic of a silicon crystal. Similar case for here, and you have another irregular geometry over here. right? But I want you to notice that at the core, still you have in this region pretty much you still have all the silicon atoms that are, you know, in that characteristic geometry where each silicon atom bonds the four silicon atoms that are around it. It's just at the surface where you have these displaced silicon atoms and this irregular surface where you have crevices and you have displaced silicon atoms and irregular geometry at the surface of the silicon crystal. Okay, and what's more to add here is that you might even introduce some impurities at the surface through these crevices. And another thing that might be something that you want to look at is that this silicon crystal could be neighboring some other compound, some other material. So as an example here, I have this, very non-ideal looking surface with crevices and stuff, right? And irregular geometry, and it has impurities, and it's also bordering silicon oxide layer, which is some other material. It's not, silicon crystal. So all of this is to just emphasize that, in reality, these surfaces are not ideal. These surfaces are not going to be as clean as, what we had, let's say, over here, right? And so in practice, we'll have non-ideal surfaces. So all that being said, now I want you to imagine a planar MOSFET. And I want you to think about this surface over here. Is it going to be that ideal surface that's like perfectly straight and no non-idealities at all, no impurities, nothing? No, right? In a typical fabrication process, again, this surface might not be as clean as we imagined it to be. And so what happens, this charge trapping phenomena is basically what it says is that whenever you have these impure and irregular surfaces, when electrons pass through, they might get stuck into the crevices of this imperfect surface. And they might get the electrons or the charge carriers might get trapped at a certain point in time, and they might get released from this surface and continue on their journey at some other point in time. And so this trapping and releasing of the charge carriers or the electrons, let's just say as charge carriers, this trapping and releasing of charges is distributed in a way that gives flicker noise its 1/f profile. So, this profile here. So that trapping and releasing of charges, that's what causes, that's what gives flicker noise its like distinct, 1/f profile. And so, yeah, that's basically the cause of flicker noise and one of the common explanations for why it happens. And so if we want to lower the flicker noise in a device, what do you do, right? So one common technique is to just make the MOSFET bigger in size. And what happens is that if you make the MOSFET bigger in size, then you're increasing the capacitances, particularly the gate capacitance. And that gate capacitance helps you to smooth out this, trapping and releasing of charges at the surface. And so it basically lowers the flicker noise corner. And so if you want to lower the flicker noise, just make your device bigger. That's one of the most common techniques in the textbooks that I've seen for flicker noise. And just as a last note on flicker noise, I want to mention that so far we have, talked about how flicker noise only, it's only contributing at lower frequencies, but that is not always the case, depending on the circuit. So as an example, when you're designing VCOs or oscillators, one of the common things that happens is the flicker noise at low frequencies gets upconverted to a higher frequency or even RF frequencies. It might get upconverted to a band of interest. And when you design an oscillator or a VCO, you might see that that flicker noise upconversion is actually causing your phase noise of the oscillator to go higher, which is something that is undesirable. But anyway, this is just to mention that flicker noise is not just a concern for low frequencies. Depending on the design, for example, in VCOs, and actually it also happens in some architectures for mixers, that flicker noise gets upconverted to a band of interest, and it basically reduces your performance, or it could reduce your performance at higher frequencies. So that is pretty much it for flicker noise, and I'll see you in the next video. Cheers.